information from Toptal.com. So this shows us different types of sorts that we've learnt about: insertion sort, selection sort, bubble sort, but also several other more complex algorithms that we haven't looked at, like merge, heap, and quicksort. And when I play this, you will see how the algorithm would go through an array and sort everything. Now there's a few different initial conditions here, different types of arrays. First, random. So these arrays are all set up in a random way. The numbers, which are represented by like lengths here, are completely at random. The second initial condition here is nearly sorted. So all of these arrays, you can see, are almost already sorted. They just need a little bit of tweaking. The third is completely reversed. The array needs to be from the smallest to the largest. Right now it's the largest to smallest. And the final one has some repetition. So you can see some lengths are the same. There's very few unique numbers in these arrays. They're all very similar. So when we play all, we can watch this red arrow go through, and we can see that nearly sorted was done very quickly on some, not so quickly on others. Insertion, selection, bubble were the last ones to finish up, and there were some faster ones over here. And if we keep looking, do this one more time. So some were really fast with nearly sorted, and some not so much. Completely reversed, same idea. Insertion sort did pretty good out of the three that we learned. So in general, we want to know what type of algorithm for sorting would be the best choice for us, or what type of algorithm to do anything is a good choice. Not only do we want a program to accomplish what we want it to accomplish, we also want it to accomplish its purpose in the most efficient method possible. So maybe if you knew that you had a big project, you were taking a database and reversing the order on every single thing in the database, then maybe you would pick the best for data that's completely reversed. So in this case, maybe we want a shell sort. I think that was the first one. On the other hand, if you know that your data has a lot of repeats, maybe you're doing something with statistics and it has to do with repeated numbers that come up a lot, maybe it's income of Canadians, something along that lines, then maybe a different algorithm would be better. What seems to be fast here? The quicksort 3 was pretty good, insertion wasn't bad, I think shell merge were pretty fast, but maybe selection sort wouldn't be the best choice in that case, as opposed to completely random, where if you're trying to decide between insertion, selection, bubble, most of the ones over on the right were the fastest, but insertion did better than selection and bubble. So if those are the ones that you were familiar with, maybe you would choose insertion. So this all just means that we need some sort of a way to figure out our best choice for an algorithm. And there's a couple different ways we do this. One way is looking at the time. So what we're just looking at here really focused on time. We can also look at the space. How much memory does it take for an algorithm to run? Is it really efficient with the number of variables it instantiates? And does it require a very large array, a very small array? Is it smart about how it's using things? Does it make a whole bunch of copies of arrays that are unnecessary? That's something we can definitely look at, is the space on the computer that the algorithm would take. However, we are going to focus on the time. How long does it take? Just like this visualization focused on the time.